The black cloud,
The black flag,
the black cloud,
the black flag. This is to my dearly beloved niggas that's rugged, no bullshit, and life is getting stressful on my nugget. Used to say fuck it, now my heart bleeds. I try to relieve my dog see, but I believe
What's going on, and welcome to another awesomely interesting, and I say that only half joking, video about vectorization. Now, you're probably feeling something a little bit different is going on, and there's a good reason for that. I had to think about it, and I was thinking to myself, like, if you're trying to get people excited and like really into something, like what's the best way to do that? And I thought about it, and it turns out that it's obscure underground hip hop from the mid 1990s as played on Stretch and Bobbito. So if you feel a little bit more hyped to learn about vectors, that would be why. All right, so there's going to be a medium-length video about mixing scalars and vectors, that thing that people do when they first vectorize their code, and then they wonder why it's orders of magnitude slower when it should have been about 4 times faster. All right, hope you enjoy it. So everything we do from this point on is going to be based on this calculation, which the clever, astute math programmers among us will recognize as not even remotely relevant, useful, or used for anything that you will ever see in the real world. So we're going to take a look at this, and we're going to look at it on every CPU that you will see as a game developer. And luckily there's only 3. There's PowerPC, there's the SPUs, and there's ARM. Those are the only things that you'll deal with this current generation as a game developer. Who knows what'll happen next gen with the Xbox 720 and whatever. So for those of you who don't have the eyes of a Lisp programmer, I'll break this down into separate lines just so you can understand what's going on and parse it better. So we have a horizontal add of some vector v2. A horizontal add is nothing more than x plus y plus z plus w. Something you'd see in a dot product. It's used for other things also. So we're going to take that scalar float that the horizontal add returns, and we're going to insert it into another vector, v1, which is as simple as doing something like that. Then we're going to go ahead and add s is some scalar, and iy, the vector that we just made. So a scalar times, or a scalar plus a vector doesn't really make sense. So you have to take the scalar, duplicate it 4 times to make another vector, and then add it. So that's how we're going to do this vector scalar add. And finally, we're going to take that vector, we're going to extract the y value, and we're going to return it, which looks like this. So let's go ahead and take a look at what this would look like on the PPU. So what you're looking at right now is the PPU version. The 3 columns in the center, the one on the left of that, V0 through V31, are your vector registers, and they're the registers that we basically do vector operations with. The column in the middle is memory. Now, remember, when doing optimization, memory is the enemy. Keep what you can in registers. Try to do as few loads and stores as possible. And the thing on the right are your floating point scalar registers, completely separate from the general purpose registers, completely separate from the vector registers. The thing on the left is the assembly. Now, remember, never judge code by how many instructions it is. Don't look at it and say, oh, you know, that's a ton of instructions. That must be really slow. Or, hey, it's only a few instructions. It must be fast. Definitely try to look at it and understand what's going on. And if you do that, you will see that this code sucks by any standards. So let's get started and take a look at why and what the PPU is doing. Okay, so we're going to start here with this STVX, which is going to take the vector that's in V31 and go ahead and look at the registers. You'll see it there in V31, and it's going to store it out to some address in memory. Don't worry about where or what points to what. Just for now, we'll just show you the animation of it going to memory. Okay, now each cell in memory is actually 1 word, so 4 words per vector. We store it out that way. Okay, the next thing we're going to do is an LFS, which is going to be a scalar load from some memory address into floating point register 0. Okay, turns out to be the y component of the vector we just stored. We're going to do the same thing with the x component. Now, we're going to take those 2 things we loaded and we're going to add them together. So I think you see where we're going with this. This is the horizontal add, and we've just added the x component and the y component of the vector together. Now, obviously, we have to do z and w. So here we're going to load z into register F11. We're going to load w into register F12. We're going to load the previous sum with the z component, and we're going to add that thing we just added right now with w. Okay, now don't freak out about the pointer jumping like that. There were no actual jumps in the code. I'm just showing you logically the instructions that correspond to the horizontal add. So that's basically it. Why did we have to go from vector registers to memory to scalar registers? Why couldn't we just go directly from one to the other? The answer turns out to be that on this particular architecture, there is no direct path between different register sets. You have to go through memory. So why is this bad? If you were doing this in scalar code, you know, x plus y plus z plus w is just adding 4 values that were probably already in floating point registers. But you took that, which should have been 3 adds, and you turned it into one store plus 4 loads plus another store plus another load, just to get everything in between the register sets, which is you're going to end up with something orders of magnitude slower than you would have had if you had just used scalar code to begin with. Now there's some ways around it, and I'll show you that eventually, but first I would like to take a look at what the vector insert looks like in assembly. So vector insert and vector extract are two things that you see a lot, unfortunately, in vector code. They usually take the form of myVector.x equals 5, where you're taking a scalar float and you're storing it to one lane of the vector. Or if you're doing an extract, you could do something like return 7.3 times myVector.y. And it's really one of the slowest things you can possibly do, and if you can avoid it, it's a good idea, and I'll show you why. So another thing you should know about loading and storing is that when you load something into a vector register, you can't just load one float. You have to load quad-word aligned quad-word. And that actually becomes a little bit problematic, because when you take your scalar float and you write it out to memory, you then have to take that chunk and read it into a vector register, which means that the data in there has to be valid, which means you have to previously have stored the vector out to memory, which is exactly what we're about to do. So here we're taking the vector in V30 and we're storing it out to memory. Now we're taking some calculated value, in this case our horizontal add value that we stored in F13, then we're going to store that out to memory in such a way that we overwrite the y value. So we're going to insert a scalar into the y of this vector. And now, from this point on, we basically have to take that vector, or that memory, and then load it back into a vector register, which is what we're going to do next with the LVX. Again, not a simple operation. It required one store, then another store, then another load. So 2 stores and 1 load. So definitely something we would like to avoid if possible. And again, I'll show you how in a little bit. And there is the load, or that would have been the load back into the vector register if I had actually made an animation for it. Now we're going to take a quick look at how the SPU does the horizontal add. The SPU doesn't have separate register files for integers or for floats or for vectors. It has one register file, all vectors, 128 of them. So it's really cool. So you don't have to worry about the cost of transferring things between register sets, because there are no scalar registers except for some special purpose ones, but that's not really what I'm talking about here. So the SPU is going to do it in the following way. We're going to take the original vector that we want to do the XYZW horizontal add of, and we're going to take that input and rotate it by 4 bytes, or 1 word, or 1 vector element. Things that are rotated out of the left come back in on the right. Now we're going to take the original input again and rotate it by 8 bytes, or 2 vector elements, giving us this. Now we're going to take it and do it by 12 bytes, or 3 vector elements. Now take a look at the first lane of each vector. If you notice, it's 8675, the same as we had 8675 going across the first one. So now we can actually just do FA as your add. So we're going to do 1 add, another add, another add. We could just do 3 vector adds and get the sum. So now, if you notice, because of the rotation, the way everything lines up, we get the same value in every lane. And because of that, there's a slight optimization we can do in the next step, but the compiler didn't recognize that and didn't go that route, but that's not important. So that's it. It's just basically rotating so that lanes happen to line up, and then just doing regular vector adds, and that's how you would add X, Y, Z, W in a horizontal add. Vector insert on the SPU turns out to be even easier than the horizontal add. So we're going to do it with an instruction called shuffb, which stands for shuffle bytes, and hopefully it will be clear if I do this animation right, and if not, then I suck. So we're going to take the scalar horizontal value that we computed, which happens to be stored in a vector, and we're going to take the thing that we want to insert that value into, and we're going to put them next to each other. Now, well, technically this is, 16 bytes plus 16 bytes, a 32-byte vector. Just think of it as one long 32-byte supervector. Now, if I were to index the bytes in this vector, it would look something like this. So you have indices 0 through 31 at the top. So the input to the shuffb instruction is this first vector, this second vector, which together form that supervector, and this mask that you now see in the middle of the screen. And this is what our output's going to be. So what we're going to do, this is a byte-by-byte operation, but I'm going to show it to you one word at a time, otherwise the animation would take too long, is we're going to look at the index in this mask, 16, then 17, then 18, then 19, then 0, then 1, then 2. And we're going to find that index in the supervector above, and we're going to steal the byte that it corresponds to and insert it into this vector. So looking at the first four, because we're going to do one word at a time, we have 16, 17, 18, 19. So where do you see 16, 17, 18, 19? Right up here. So we're going to take that 1 and we're going to put it down there. Now again, you can do this on a per byte basis. You can steal a byte from here, a byte from there. It doesn't have to be 4 contiguous bytes. But obviously this is what we want because we're trying to steal one word from whatever vector slot that we're in. So next is 0, 1, 2, 3. We have 0, 1, 2, 3 up there, just 26. Now, by this time, you probably see what's going on. 24, 25, 26, 27, that index is up there, and that's a 3. And then 28, 29, 30, 31 is this 4 down here. Now, there's some other special values that don't directly correspond to byte indices in that supervector up there, but that's not 100% important for right now. So what did we do? We basically selected from 2 different vectors the elements that we wanted to keep, and then we chose the scalar that we wanted to insert and just put the indices for that in the mask. Now, this mask has to come from somewhere. If you're lucky, you might be able to use some instructions to generate it on the fly, otherwise you're going to have to load the mask in from memory. So you don't want to do one of these with a different mask all the time. If you could load one mask and keep it in a register and then do a bunch of these shuffles, that would be a much, much more efficient way to do it. Now, like I said before, there was a slight optimization. Because 26, 26, 26, 26 is broadcast to all 4 lanes, we technically, instead of doing a shuffb, which has a latency of 4 cycles, we could have done a vector select, where you just basically go bit by bit and select either the bit from the first vector or the second vector, depending on what the value of the mask is. That happens to be a 2-cycle instruction. You may want to use it, you may not want to, because it's even and the other shuffb is odd. So depending on which pipeline is more busy, you might want to choose the one with the longer latency if it helps you schedule things in better, or if it helps you dual issue better. So that's about it. That is how you do the 2 operations on the SPU, and now we're going to move on to the mother of all CPUs. Well, not really, but it's just my personal favorite. So one of the coolest things about Neon on ARM is the register set. So like many vector CPUs or vector processors, it has quad word registers. Now on Neon, these go Q0, Q1, Q2, Q3, all the way up to Q15. So there are 16 vector registers. Now, the cool thing is, you also have, instead of 4 words, you also have double word registers consisting of each one a double word. Now the thing is, these actually alias the quad word registers. They're just another way of accessing the same register. So I can go ahead and compute some XYZW result into Q0. And if I only want to overwrite Z and W, I can actually do some operation that uses D1 as its destination register, because D1 is the exact same thing as Q0's Z and W. They alias each other, they overlap, they're the same thing, they're just different ways of accessing the data. So now, let's say you compute something into D1, some double word result, and you want to access one particular scalar out of that result. Now, the double word registers break down with the bracket operator, so you have D0 bracket 0 and D0 bracket 1 are the ways to access the two scalars in D0. And D0 is the same thing as Q0's X and Y. So just look up and down and you'll see what occupies the same space. And then you also have scalar registers, which are the same thing as the D0 and D1, all that bracket stuff, except usually saved for scalar mode, which we'll talk about in a little bit. And now I will actually show you the ARM version. Word to mother, that is the actual ARM version. Now, it's beautiful, it's elegant, it's compact, it's expressive, and it's incredibly fun to write. So I'm kind of psyched to show this to you. So starting off, you have VPADD. That is the horizontal add. There's an instruction for it, but it only works on a double word at a time, so we have to do 2 of them. Okay, so let's take a look at the result. The result of that final VP add stores its result in D10. Well, what does D10 look like? D10 and D11 are the same thing as Q5, as the same thing as D10 bracket 0, D10 bracket 1, D11 bracket 0, D11 bracket 1, and S20 through S23. So when we take a result and store it out to D10, S20 is going to be affected, D10 bracket 0 is going to be affected, the X component of Q5 is affected. Now, to be completely fair, S21 is also affected, but because we're not going to use that result in a subsequent computation, I didn't make it red. But if you think of red as being stuff that's modified, then S21 should be red, and D10 bracket 1 should also be red, because the whole D10 register was written to by that vector pair horizontal add operation. Okay, so we're eventually, if you look at the last instruction, the VAdd, we're eventually going to need the scalar that we computed with the horizontal add. We're going to need to insert that into the Y component of Q6. So let's take a look at what Q6 looks like, and I went ahead and put a green X in the Y component where we want to insert. So what would affect that Y component? Well, a write to D12 would affect it, a write to D12 bracket 1 would affect it, and a write to S25 would affect it, because those are all the same thing. But what we end up doing is taking D10 bracket 0, which you will see in red on the left as the scalar value that we computed from the horizontal add, and storing it in an ARM core register, R3. We then take R3 and store it out to D12 bracket 1, which if you look in the right is on green. That's the target that we wanted to do in order to insert it. So why did we do this? I mean, if you have these great, aliased registers, why would you even go to, a completely different register set, the general purpose registers, and then back again to a vector/scalar register? Well, as best I can tell, if I were to do a move from a scalar float register like S20 to another scalar float register, that would be using neon in scalar mode. And when you switch between vector mode and scalar mode, and then scalar mode and vector mode, because it's a mode switch, there's a pipeline flush, and it tends to get expensive. Now, the second thing is that on later Cortexes, the performance penalty associated with transferring between vector registers and scalar registers is very, very small. Number one, you don't have to go through memory because there's a direct path. And number two, I think there's only a 8-cycle penalty in one direction. It's asymmetric. I think it's a different It's a different timing in each direction, but compared to a pipeline flush, it's actually better. So basically, we just move it temporarily into a core register, a GPR, then move it into the destination vector register, and boom, it's the exact same thing as doing an insert. It's just already there, and then we're free to use Q6 as a whole vector, and we had just inserted to the Y. It's that cool. So looking back at the ARM example, I mean, it seems to be okay dealing with some degree of vector and scalar mixing. It even has instructions that can take a particular lane of a D word, you know, or a scalar, and multiply an entire vector by it. So it's doing okay. It's the PPU that needs a little bit of loving in this area. And one possible solution is called float in vector. Now I'm not going to insult your intelligence by showing this to you. It's basically wherever you see a float, take that float away and then put a vector there. So if you have something float x equals 5, you're going to have a vector that has to have 5, 5, 5, 5 in it. So you broadcast it across all 5. That allows you to go ahead and multiply with a vector and has the same effect, all kinds of stuff. So I went and I rewrote naively, not even efficiently, the PPU code using float in vector, and this thing on the left is what it came up with. I mean, there's one load in there, or two technically, but one of them is related to a mask. It's one load in there. It's just this beautiful block of vector code. It's a lot better than it was before. It functions very, very similarly to the way that you would see the way the SPU version functioned. So we're basically going to take the same vector, and then we're going to make stuff line up so that you can just do 3 vector adds to do the horizontal add, except instead of rotating it, we're just going to broadcast the exact same value, splat it across the vector. So we have VSPLTW, it's a vector splat, and see that constant on the end there, the comma 1? 1 in this case means Y. If we had a 2, that would be Z. If we had a 3, it would be W. A 0 would be X. So we're going to take something in V30, which you see as XYZW, and then we're going to repeat Y all across the vector, or splat it. Now we're going to do the same thing with 0, which is X, and we're going to do the same thing with 2, which is Z, and finally the same thing with 3, which is W. And then obviously we can just add them like you would any other vector, and that's how you get X plus Y plus Z plus W, or the horizontal add. The way that we're going to do vector insert with float in vector is what I was talking about before with the SPUs, where I said there was a select instruction that would go bit by bit and allow you to select either a bit from input 1 or input 2, depending on what the mask bit was. So that would be VCell on the PPU, and it looks a little something like this. So you have one input vector. This is the thing that we want to insert some value into. Now we've got another input vector, which is the scalar that we just calculated. So 26, 26, 26, 26. It's the horizontal add, you know, broadcast splat across the whole vector. And finally you have a mask. So the way that this works is you go through the mask bit by bit by bit, and if the bit is 0, you select whatever the bit is from the first input. If the bit in the mask is 1, you select from the second input. So we're going to put our output down there. Now again, I'm going to show you this word at a time, because if I were to go through this bit by bit, number 1, I couldn't have a mask with 128 bits. I'd run out of room, and number 2, it would take forever. So this right here, if you look at it in binary, is going to be 32 zeros, which means that for 32 bits, we're just going to select whatever bit happens to be in the first input, essentially copying that whole first vector word into the output. Now here we have FFFFFFFF, which is really just 32 ones. So because all these bits are 1, we're essentially just going to copy the word from the second output. And then same thing here, all zeros, so we pull it from the first input, and then all zeros again, so we pull it from the first input. So essentially, what did we do? We just selected either a word from the first one or a word from the second one, depending on what the mask was. That's why things had to be lined up, or you had to have the values splatted across to make this work, instead of using ShuffB like you did on the SPUs. Now, a couple things to warn you about float and vector. It's not a miracle cure-all. It doesn't really help with everything. It increases the pressure on the vector registers, because before you only had to store your actual vectors in vector registers, and all of a sudden you have these things that used to be floats but now live in vector registers. So you increase the pressure on that, may be problematic. If you're writing a float and vector out, remember that you can only read and write on vector processors. You can only read and write a quad word at a time, a quad word aligned. So I can't just pick a scalar and then serialize it out into some random struct. I have to write a vector at a time out into memory, which could be weird in some cases. These things are slow to create. All the problems that you had taking a scalar value and inserting it and putting it into a vector, you have with this also. The trick is to create one of these and then just leave them around for a long time, so that you don't have to, constantly build these on the fly. If you build these on the fly from scalar floats, you're going to have the exact same problems that you had before. And sorry, I got a little bit ahead of myself. And then we actually write the 4 from that first input out. I thought that I would close with another solution that it is just unbelievably, incredibly useful in a large number of situations. However, this video is already too long, so I'm going to have to dedicate an entire video to this alone. However, I do want to give you a little bit of a taste of what's coming up. So it's called SOA, which stands for structure of array, and it's contrasted with AOS, which is what you're probably used to using, which is array of structures, where you've got a structure, X, Y, Z, W, and then you have an array of those. SOA is the opposite. So if you think about, maybe you have a particle system, right? I don't know why that's my go-to example. You have a particle system, and each particle has a position. You would store all the information about that particle's position in one vector. So you have its X position, you have its Y position, Z, W. Maybe you have 4 particles now. So you have X1, Y1, Z1, W1, X2, Y2, Z2, W2, all the way up to X4, Y4, Z4, W4. So what would happen if, instead of doing it this way, you turn the problem on its side? Right? Turn the problem on its side, huh? Okay, so you end up with something like this. And I don't know how to rotate the text, so I'm sorry if it's sideways. Now, instead of a vector containing an X, a Y, a Z, and a W for one particle, you have the X values for all 4 particles, followed by another vector which has only the Y values for all 4 particles, and then the Z values for all 4 particles, and the W. It's basically, if you thought of it in its original form as a matrix, it's kind of like a matrix transpose. You actually get this for free, or not for free, for 1 cycle on ARM Neon. There is free transposing between AOS and SOA on load. You just kind of get it, and it just puts it in the right place. It's really cool. So we're going to discuss this in another video, the drawbacks, the positive things, what it's used for, and why it's freaking awesome. And cool, hope you enjoyed the video. I apologize for it being so long, and I apologize for my voice being jacked, because I am just getting over food poisoning. Alright, yeah, if you got any questions or requests, let me know, and hopefully I can make another one soon. Thanks.